Hello everyone, this is the chapter 3 Frappy. So, what's happening is, two students are at a flower shop and they randomly select 12 carnations. When they got home, they prepared 12 identical vases with the same amount of water in each vase. They put 1 tablespoon of sugar in 3 vases, and 2 tablespoons of sugar in 3 vases, and 3 tablespoons of sugar in 3 vases. In the remaining 3 vases, they put no sugar. So there's a group of 3 for every sugar amount. After the vases were prepared, the students randomly assigned 1 carnation to each vase and observed how many hours each flower continued to look fresh. A scatter plot is shown below. So sugar is definitely going to be my explanatory variable, or x, and freshness is definitely going to be my predicted value, or y, hat. This is in hours. Sorry, I didn't print very well. So then what we have is the first question: briefly describe the association shown in the scatter plot. Anytime we have association, we always want to think of 3 things: direction, form, and strength. So these aren't things that you need to write on yours. It's just a guide. So I would say that the scatter plot shows a moderately strong, positive, linear association. So moderately strong, positive, linear, and then you always want to do your variables. Okay, between tablespoons of sugar in the water, in the base water, and the number of hours that the flowers continued to look fresh. Okay, so I have number of hours, tablespoons of sugar. So I have all 5 of those things in this description. Part B. The equation of least squares regression line for this data is y hat equals 180.8 plus 15.8 times x. Interpret the slope of the line in the context of the study. I think it's always good to make sure we understand what y hat and x are representing. So y hat in this situation is the hours of freshness. And x is the tablespoons of sugar. Now, when I look at slope, and you don't have to write this on yours, I'm just writing a little description for you. Slope is always going to be your change in y over your change in x. Now, anytime that you have the slope is like 15.8, I can always just put it over 1 because that would create that fraction that we want. And then I have to think 15.8 is my increase in number of hours, and 1 is my increase in tablespoons. So that's how I like to think of it, and then I start putting it into words. So the slope represents that the hours of freshness increases. Now I'm saying the direction is increased because this is a positive 15 by 15.8 hours per, because that's like how you say a fraction with words, per each additional tablespoon of sugar in the water. There you go. Okay, one moment. Sorry, I did close the door so you guys don't hear that. Okay, part C. Calculate and interpret the residual for the flour that had 2 tablespoons of sugar and looked fresh for 20 or 204 hours. So this is an actual data point, right? So in this case, you have basically the point 2,204, and you want to see how it compares to your y hat value. Now, so this is data, and then to find my y hat value, I would have to plug in 2. So we'd get 180.8 plus 15.8 times 2. Now, when you solve that through, you get your y hat value is 211.6. Now, I'm comparing this value here to the y value of the actual flour itself. Now, we want to find residuals here. This is a little aside, so you don't actually have to write this part. But your residual is used the letter E, and it's always the data value minus the predicted value. So to do that, in this case, you can also write it as y minus y hat, right? Now, y in this case is 204. Y hat is 211.6. So in the end, we get negative 7.6 is going to be our E value. Okay? Now, this value is telling me that if I had like my line, for example, this data point is below the line by 7.6. So that's what this is telling me in this case. And it would tell me that we have the negative residual. E shows that the flour bloomed for 7.6 hours less than predicted by the linear model. Okay. Also, sorry if you can hear other things. Gotta remember, there's other people in my home too. Anyway. Okay. So the next thing, for part D, it says, suppose that another group of students conducted a similar experiment using 12 flowers, but included different varieties in addition to carnations. Why would you expect the value, or would you expect the value of R squared for the second group's data to be greater than, less than, or about the same for the first group's data? Now, I'm just going to put a little recall on this for you because there is some information that we haven't talked about in a while. So if you can just recall to yourself, here, let me get an extra piece of paper to write this on. If you can just recall to yourself what all of these things are from this chapter. E is residual, which is the difference between a data value and the expected value. R is your correlation coefficient. And that tells you how linear a data set is on a scatter plot. And then R squared is called your coefficient of determination. Now, this coefficient of determination, this is my realtor, sorry, she gave me a pad of paper. Anyway, so the coefficient of determination is found by doing this. R squared equals 1 minus the sum of all residuals squared divided by the sum of all of the y minus the mean of y values. Now, this situation, you have to think about as the residuals get bigger. So like if I have my line, right? As my residuals, so if they're like this, they're pretty close, kind of like the data we were just looking at. But now we add new flowers. What if that flower's all the way down here? This is a much bigger E value, or it could be all the way up here. And that's going to drastically increase my residual amount. And what that's going to do is when I get my residuals squared, it's going to increase or decrease my information. Now, it's more likely that a new type of flower is not going to match the behavior of the carnations. So in general though, here, we could just say as the residuals, which is E, increase, then we'd expect R will decrease. Okay, now there is another way to think of this if you just want like a flow chart, because I know a lot of you like when I do flow charts, and I have this right here. So what we can talk about is that the variability increases, which would be less linear behavior, right, more spread out. Then the residuals will increase because we're farther away from the line. The correlation coefficient R gets closer to 0 because it's less linear. And as this gets closer to 0, and the residuals increase, it will cause the coefficient of determination R squared to get smaller. Now, this is the same idea, but in reverse. If variability decreases as it becomes more linear, then my residuals will decrease because they're closer to the line of estimation. Our correlation coefficient R will get closer to -1 or 1 because it's getting more linear. And then the coefficient of determination R squared will get bigger because the closer it is to 1, when I square it, it's going to get bigger. So this is a little flow chart. If that helps you can write it down. But using all of these ideas, we can solve this question. So what we have is we're going to say, here, let me move this up just a little bit. Okay. When a new flower is added, then the variability, which is like the spread of the data, like all of the dots, of the number of hours flowers stay fresh will most likely increase. Now this is because carnations, like if I picked a lily lasts a long time, or a daisies last a long time, versus something like a carnation, which might not last as long. So I'm not exactly sure what's going to happen, but it's definitely going to change, so the variability is going to increase. Then I'll say, this next sentence is kind of optional, but I'm going to write it down. The data points will be farther from the prediction line, causing the residuals, which is our like E square value, right? If we square it, to be larger, which will cause the R squared value to decrease. So that's one thing you could say. Another sentence you could choose instead, if you want to talk about R, the correlation coefficient, you can say, we can also say that the correlation coefficient R should be closer to 0, right? Since it will be less linear, which will cause R squared to decrease. I don't know why it got spread out, sorry. As well. I know that's more than you would probably have to write. I'm just trying to be really clear so that you understand it in the end. There you go.